In this third video on displacement, I want to take a look at circular motion. So remember we looked at this example before. This is a ball rotating in a circle, and I've brought back the vectors that we used to describe this motion this last time. And so here, with the ball started at this point here at t is equal to 0, and then it rotated 50 degrees every tenth of a second. So a tenth of a second later, it was here, a vector that I'll now call r sub 1, and then tenth of a second later, it was another 50 degrees, which is there, a vector I call r sub 2, then here, then here. So you can sort of visualize in your head this ball on a string going around in a circle, and then it just keeps going around and around, and the yellow position vector tracks its motion so it can describe the location of the object at any point in time. So now we want to look at the displacement vector, and so we're going to look at the displacement vector between these two vectors. Again, a displacement vector means we choose 2 points in time, an initial time, 0, and a final time, which in this case will be 0.1. And from those 2 times, we can evaluate the 2 vectors, which are here. And from those 2 vectors, we can calculate a displacement vector, which I'll call delta r sub 1, which is in this case r1 minus r sub 0. And you can add them graphically, as we did in the last 2 videos. But we also know, and I'm just going to do it directly here, that this displacement vector points from the location at the initial time to the location at the second time. So this is delta r1. And now if we continue, where the second displacement vector then is r2 minus r1, which means, and now I'm looking at the displacement vector between these 2 vectors here and here. The 0.1 is now the initial time, 0.2 is now the final time, r2 is now the final vector, and r1 is now the initial vector. And so this displacement vector is r2 minus r1. And that vector then points from r1 to r2. This is delta r2. Delta r3 then is the third vector minus the r sub 3 minus r sub 2. Given this notation, it's going to point from the tip of r2 to the tip of r3. There's r3. And if I continue with this definition, I have, here's the displacement delta r4, here's the displacement delta r5, here's the displacement delta r6, here's the displacement delta r7. Now, I didn't include yet this last one, and now it starts to go around on itself. And so if I did delta r8, that would be about here. This is going to be r sub 8, which is the radius vector. These should have vectors. I sort of lost my position vector notation there. At 0.8 seconds, then where it's already gone all the way around the circle, and so the position vector here would look like that, and that would be delta r sub 8. And so in circular motion, how we approach it is just like how we approached everything else. For each displacement vector, there are 2 important points in time, the initial time, final time. That gives us an initial vector, final vector, and the displacement is the final vector minus the initial vector, which is the same as adding the negative of the initial vector. And from on our position diagram, it points from the location at the initial time to the location at the final time. The interesting thing to note about this circular motion here, in fact, because it always changes by an equal angle over an equal time, that the magnitudes of all of these vectors are the same. And so because it is going around in constant motion, and so the angle over each unit of time is the same, the magnitude of the displacement vector is the same for each pair of vectors. And while the direction of the displacement vector is changing as the particle goes around in the circle, the magnitude is in fact the same.